Okay, let's jump right in. You've probably noticed AI showing up in more and more places these days, from powering those helpful chatbots to creating jaw-dropping art.
Yeah, it's everywhere.
But there's a particularly fascinating corner of AI development happening in virtual worlds, like video games.
Mhm.
The quest to make AI that doesn't just play the game well, but acts convincingly like a human player.
It's a goal that sounds straightforward, maybe, but it's actually much harder than it sounds. It presents some really deep academic and technical challenges.
Right.
And, the ability to distinguish human behavior from artificial behavior in these digital spaces, that has implications far beyond just gaming.
Absolutely. So for this deep dive, we're going to unpack exactly what makes creating human-like AI so difficult. We'll explore the significant hurdles researchers and developers face, and then we're going to spotlight a really innovative method proposed in a recent academic paper. This was presented at a major conference, AMAS 2025.
Right, AMAS, good conference.
And it tackles the crucial question. How do we even measure if we're succeeding? How do we know if an AI is really acting human?
Yeah, that paper by Swiechowski and Slezak, it dives deep into two core problems in this field. First, just the immense difficulty in modeling and implementing AI that genuinely acts like a human.
Capturing our quirks and limitations. Right?
Exactly. Our strategies, our flaws, all of it.
And second, and this is where their novel contribution really comes in, how do you objectively evaluate that human likeness? How do you design a test that tells you with confidence if an AI is behaving like a person or just a very sophisticated bot?
And their empirical study proposes a machine learning approach that is, well, remarkably effective at doing just that.
Okay, so consider this your shortcut to understanding the bleeding edge of this fascinating field. Let's start by digging into those academic and technical challenges. Why is making AI behave like us in a complex digital environment so incredibly hard?
Well, one of the most fundamental academic hurdles, it really stems from the sheer complexity of the games themselves.
So,
Specifically, what researchers call the action space and state space. In complex strategy games, just think about the almost infinite number of possible moves a player could make at any given moment, and the astronomical number of different game situations that could arise from those moves.
right, you hear terms like branching factor, how many choices there are from one point,
Yeah.
and state space complexity, which is just the total number of unique game states. It gets huge fast.
It does. And even for seemingly simpler perfect information games like chess or Go, reaching human championship level required AIs like Deep Blue or AlphaGo to use immense computational power.
Just brute forcing the search space, essentially.
Well, very sophisticated search, but yes, searching through vast possibilities.
Okay.
Now, when you move to more complex real-time strategy games like StarCraft 2 or multiplayer online battle arenas like Dota 2, the complexity just explodes even further.
Right. More players, hidden information.
Exactly. AIs like AlphaStar or OpenAI 5, which could compete at the highest human levels, they relied on massive clusters of specialized hardware and, tons of training data.
Not something you can run on your average gaming PC.
Definitely not. So simulating nuanced human-like reasoning, planning, and intuition in these environments, on a standard consumer PC where most commercial game AI has to run, it's simply computationally prohibitive with current methods.
Okay.
The AI needs sophisticated ways to navigate complexity without unlimited resources. You can't just search everything.
And it's interesting, it's not just too much complexity that's a problem, is it? The paper notes that environments that are too simple also make it hard to tell humans from bots.
That's a fascinating point, yeah. In games like Tic-Tac-Toe or even older arcade games like, say, Mrs. Pac-Man,
Okay.
there are only a limited number of optimal or, let's say, reasonable actions. A human player and a perfectly rational bot might end up making the exact same moves most of the time.
Because there's just not much room for variation.
Exactly. There isn't enough unique behavior or strategic depth to really see how a human player might deviate or express individuality or even make a suboptimal but understandable move.
So the environment needs enough expressiveness, as they call it,
Yeah.
enough variety in possible actions and outcomes for human-like behaviors to even emerge and be observable.
Precisely. It's finding that sweet spot between overwhelming complexity and trivial simplicity. You need room for strategy, nuance, and even errors.
Speaking of complexity, what about scaling these AIs up?
Yeah.
Games aren't always just one-on-one battles anymore. We have these huge virtual worlds.
Yes. That brings us squarely to the challenge of scale. The powerful AIs designed for 1v1 scenarios like AlphaGo or AlphaStar.
Yeah.
They simply don't scale efficiently to virtual worlds populated by thousands or even millions of diverse non-player characters, NPCs,
Right.
each needing some level of individual control and hopefully believable behavior. Think about simulating a virtual city.
You can't just replicate a supercomputer-trained AlphaStar for every single NPC walking down the street.
Exactly. Current industry workarounds often involve using much lower fidelity crowd AI for background agents, or maybe simpler rule-based systems.
Okay.
Research is exploring more scalable approaches for larger numbers of more sophisticated agents, like using architectures based on, say, utility AI, combined with decision-making cycles like OODA loops, observe, orient, decide, act. But achieving sophisticated, believable behavior for a large population of unique agents simultaneously, that's still a huge computational hurdle.
Another major academic challenge the paper highlights is incorporating realistic biological constraints.
Yes.
AI doesn't have a body or a brain like ours, and that lack of human limitations makes them seem inherently non-human, right?
This is where the insights get really interesting, I think, because it forces us to consider what makes human behavior distinctive because of our physical and cognitive makeup.
Okay, give us some concrete examples that the paper mentions. What kind of constraints?
Well, take visual perception. AI often gets direct access to the game's internal data. It knows exactly what's happening everywhere on the map, instantly.
Which humans definitely don't.
Right. Humans rely on vision, which is limited by line of sight, obstacles, focus, the need to actually look at things. The paper references an old example from Unreal Tournament 2004, where bots were observed collecting items hidden behind walls without even turning to face them.
Dead giveaway.
Totally. So recreating realistic, imperfect visual perception just from raw game data is surprisingly complex. You have to simulate not knowing things.
Or memory. Humans forget, we prioritize, details get fuzzy over time. AI could theoretically remember everything perfectly.
And perfect memory, again, makes them seem non-human. Designing AI memory systems that introduce realistic forgetting or maybe prioritize recent or important information while letting less relevant details fade.
While still letting the AI function effectively.
Exactly, all while still allowing the AI to achieve its game goals. That's a significant design challenge. Academic research has looked at this specifically for creating more believable NPCs.
And what about reaction times? We often see bots with lightning-fast, superhuman reflexes.
Yes. AI often has virtually unlimited reaction time. Implementing human-level physiological limits on how quickly an AI can react to an event or how rapidly it can execute a sequence of actions. That's another technical hurdle researchers tackle to make bots more believable.
The paper also mentions introducing other constraints from research like confusion, basically making errors, or even simulated tiredness. It sounds like adding these human-like flaws actually makes the AI less effective at playing the game optimally.
That's the core trade-off they discuss. It's fundamental. To be believable, AI needs to exhibit human-like limitations. But to be a competent opponent or character in a game, it needs a certain level of performance.
It's a balancing act.
It really is. Finding that balance is tricky. If you make the AI too competent, it might rely on superhuman abilities like pixel-perfect aiming or perfect knowledge, which makes it unbelievable in a different way.
So it's not just about making AI good at the game. It's about making it good at the game like a human would be, including the imperfections.
Exactly. The flaws are part of the pattern. They're part of what we recognize as human.
Okay, another area. Handling uncertainty. Games often have hidden information, like the fog of war in strategy games or random elements. Humans make inferences under uncertainty, often, well, imperfectly.
Yeah, and this presents what's called a combinatorial explosion for AI in games with hidden information. The number of possible game states, given what's unknown, it just grows exponentially.
Right.
And while AI can be designed to handle uncertainty and probabilities very efficiently, sometimes even perfectly if they do it too well,
Human players notice.
they perceive it as cheating AI. You see that complaint all the time online.
Yeah.
So the academic challenge here is simulating human-like reasoning processes for making inferences under uncertainty, which, you guessed it,
Computationally intensive.
and it impacts how effectively the AI can actually play. It might make worse decisions from a purely optimal perspective to seem more human.
Wow, okay, that's a really comprehensive list of roadblocks. Complexity of the world, scaling issues, simulating physical and cognitive limits, handling uncertainty. Given all that, how do we even train an AI to navigate this minefield in a human-like way?
Good question.
Machine learning, especially using human game data, seems like the obvious path, maybe.
ML is definitely a promising approach, yeah. And training on large data sets of human gameplay is key. But the paper details technical challenges here, too.
Data volume, I'd assume, is one.
Huge data volume is needed, often millions of gameplay sequences. And that data might just not be available during the critical stages of game development, before release.
Right.
Plus, human players are incredibly diverse. Training on general data might just produce kind of average behavior, not necessarily believably human behavior that captures the variety and individual quirks we see.
And training these models must be computationally demanding.
Incredibly so. Training large deep learning models, especially using reinforcement learning in these complex action spaces, is notoriously sample inefficient. It requires significant computational resources, time, money. And finally, there's a subtle but important difference in control inputs. Most game AIs operate at a high conceptual level, move unit X to location Y.
Abstract commands.
Right. Human behavior, however, emerges from sequences of atomic, low-level inputs, individual mouse clicks, key presses, joystick movements.
The actual physical interaction.
Yes. Training AI to simulate these low-level inputs to produce emergent, human-like movement patterns or targeting behaviors or tactical maneuvers, that's a distinct technical challenge. It's much harder than just telling it where to go.
So it's not just learning the optimal strategy, but learning the human way of executing that strategy, including all the messiness of low-level control.
Exactly. It's a whole other layer of complexity that goes beyond just high-level decision-making.
Okay, so we spent a good chunk of time on why it's hard to create human-like AI. But as you mentioned, the paper has a significant contribution on the flip side. How do you measure it? How do you detect believability?
Yes, and this is where the paper presents its really innovative approach using machine learning, specifically deep learning, to build a model designed to distinguish human players from bots.
And they tested this in a specific game environment.
They did. They conducted their empirical study in a tactical game called Tactical Troops, Anthracite Shift.
Okay, tell us a bit about that game.
It's a 2D, turn-based strategy game. Players command a small squad of units on a map. Units have continuous movement, use action points for things like shooting, using gadgets, or setting up Overwatch mode.
So tactics are key. Positioning, timing.
Absolutely. Positioning, timing, unit abilities, all critical. It provides a good testbed for complex decision-making.
And the AI already in that game is what they're trying to distinguish from humans.
Precisely. The game uses a hybrid AI. It combines utility AI for the more strategic, longer-term decisions, and Monte Carlo tree search, MCTS, for the immediate tactical choices, like where to move next turn or who to shoot.
Okay.
The researchers' goal was to see if a machine learning model could reliably tell when this existing hybrid AI was playing versus when a human was playing.
So what was this innovative machine learning model they developed? You mentioned deep learning.
Their approach uses a hybrid deep neural network. It combines two powerful types of networks, a convolutional neural network, a CNN.
Okay, like image recognition uses.
Exactly. And a recurrent neural network, or RNN.
Which are good at sequences, like text or time series.
That's right.
Okay, so let's break down the academic rationale here. Why use both? What's the innovation in combining them?
This is the key academic insight of their evaluation method, especially for this type of tactical game. The CNN component is designed to excel at processing spatial or visual data, things you'd represent on a map. They fed it inputs representing different layers of the game environment, the layout of obstacles, the positions and health of all the units, locations of strategic points, stuff like that.
So it's like feeding the network simplified images of the game state.
Pretty much. Just like CNNs are great for image recognition, this part of the network is great at understanding the layout, the spatial context, the relationships between elements on the map.
So it sees the battlefield, understands the positions.
Exactly. The RNN component, on the other hand, is designed to process sequential or numerical data over time, basically. The history of what happened turn by turn.
Oh, okay.
They tracked 10 specific numerical features for each player at every game state.
Like what kind of features? Damage dealt, gadgets used?
Yeah, things like turn number, damage statistics, dealt and received, friendly fire events, usage of specific items like grenades or cloaks, status changes of units like being suppressed or wounded.
Things that change over the course of the game.
Right. This part of the network processes the sequence of these events as the game unfolds. It captures the temporal dynamics, the flow, the history of player actions.
So the model isn't just looking at a single snapshot or just summary stats at the end. It's watching the game develop turn by turn.
Yes. And that's absolutely crucial to its effectiveness. The full model processes a sequence of the last 250 game states.
Wow, that's quite a history window.
It is. And it combines both the spatial data captured by the CNN and the sequential numerical features processed by the RNN. This multimodal input is the key.
Multimodal meaning using different types of data?
Exactly. It allows the network to learn really complex patterns that involve both where things are happening on the map and how the player's actions and the game state are evolving over time.
Okay.
It's this combination that's powerful for detecting those nuanced gameplay behaviors, the subtle things that distinguish humans from bots.
That sounds like a very sophisticated way to analyze gameplay. So, what kind of results did this hybrid network achieve? How well did it work?
They used a standard evaluation metric in machine learning called the F1 score. It's a good metric because it balances precision.
Which is how many it said were human that were actually human.
Right, and recall how many of the actual humans playing did it correctly identify. You want both to be high.
Okay, so what was the score?
Their hybrid CNN plus RNN model achieved an F1 score of 0.92.
0.92. For distinguishing humans from bots in a complex tactical game, that sounds remarkably high.
It is remarkably high, and it represents a dramatic improvement over previous attempts. For comparison, a model tested earlier in tactical troops using a different technique called XGBoost with only summary numerical features, that achieved an F1 score of just 0.58.
Wow, so 0.58 to 0.92. That's a huge leap.
It really is. It shows this multimodal deep learning approach is significantly more effective at capturing those subtle patterns that give away whether a player is human or not, at least in this environment.
And they show that using just the CNN part or just the RNN part wasn't as good, right? The combination was important.
Correct. They tested the components individually. The RNN-only model achieved 0.88 F1, still good, suggesting the sequence of actions is very informative, but not as high as the combined model.
Okay.
And the CNN-only model, just looking at the spatial data, was much lower, at 0.59 F1.
So looking at the map alone isn't enough.
Not nearly enough. This clearly demonstrates that while the sequential data is highly informative, combining it with the spatial context via the CNN significantly boosts the model's ability. Particularly, it improved precision, reducing those false positives where a bot might be misidentified as human.
Got it.
The synergy of combining these different data types processed appropriately is really the key academic innovation here for the evaluation task.
So the big academic takeaway is that for analyzing this kind of complex gameplay, you really need to look at both the where the spatial stuff and the when or how the sequential actions using a multimodal approach to reliably spot the difference between human and AI players.
Precisely. It validates the hypothesis that sophisticated patterns revealing non-human behavior do exist in AI gameplay, and they can be detected effectively if you use the right analytical tools like this hybrid network.
All right, so we've seen the deep academic and technical challenges of creating human-like AI, and now this really innovative method for detecting it. What are the broader implications of this research? Not just for game developers, but maybe for you, the listener, and the wider world.
Well, one exciting implication the paper proposes is actually using this kind of human likeness detection model as an automated quality assurance tool during AI development.
Oh, interesting. How would that work in practice? Like for a game studio?
Imagine you're developing game AI. You train your bots, right?
Okay.
Then you test them against this human likeness detection model.
Right.
Now, if the model fails to identify your AI as a bot, if it actually mistakes it for a human.
That's a false positive for the detection model.
But it's actually a success for the AI developer. It means the AI is exhibiting patterns that are convincingly human-like, fooling the detector.
Oh, I see.
You could then take the data from that human-like AI performance and use it to retrain and refine the detection model, making it even better at spotting subtle non-human traits.
Okay.
Then you go back and refine your AI player further, trying to deceive the new, more sophisticated detection model.
It creates a kind of adversarial loop, an arms race between the AI trying to be human-like and the model trying to spot the non-human.
Exactly, a continuous improvement loop. That's a clever way to iteratively push the AI towards greater believability, using the evaluation method itself as a development tool.
That's really neat. And beyond games, the ability to accurately distinguish humans from bots has some pretty significant real-world applications too, doesn't it?
Absolutely. The source points to critical uses like enhanced identity verification and sensitive online interactions.
Like what?
Well, think about online exams in education, secure transactions in finance, or even certain interactions in healthcare. Ensuring you're dealing with a human is crucial.
Yeah,
It's also vital for things like preventing online scams, detecting malicious bot activity like spreading misinformation or manipulating markets, and generally ensuring trust in digital environments.
It could even serve as a kind of benchmark, a metric for the general progress of AI itself.
That's another angle, yeah.
Hmm.
By seeing how well AI can pass these increasingly sophisticated behavioral tests designed to identify human players. And yes, potentially, this kind of research could lead to more robust next-generation CAPI-TCHAs, those tests to prove you're human that are much harder for bots to solve than the current ones.
The paper also leaves us with an intriguing open question, almost a hypothesis, based on their findings and all the challenges we discussed earlier.
Yes, they propose that there might be an inverse correlation. The harder it is to create genuinely human-like AI for a particular environment.
Like because of all those constraints and complexities.
Right. The harder that is, the easier it might actually be to develop a method for detecting whether a player in that environment is human or a bot.
Huh. So all those difficulties we talked about, simulating human biological limits imperfectly, handling uncertainty in a human-like, often suboptimal way, replicating the messiness of low-level control inputs. Those very difficulties might create observable patterns, little tells, that a sophisticated detection model, like their hybrid network, can pick up on relatively easily.
Precisely. If the AI inherently struggles to perfectly mask its non-human origins due to these deep challenges, those imperfections become signals. They become features that a multimodal analysis can detect. It's a fascinating hypothesis for future research to explore.
And to encourage that, they're even planning to host an open machine learning competition using the tactical truths data.
That's right, inviting researchers from around the world to try and build models even better than theirs at distinguishing humans from bots, using their 0.92 F1 score method as the baseline to beat.
That's a great initiative to push the field forward.
Definitely. Fosters collaboration and innovation.
So to wrap up, we've taken quite a deep dive today into the complex academic and technical landscape of creating AI that behaves like a human. We've explored the profound challenges, from simulating physical limits to handling the unknown and training these sophisticated models.
It's a really multifaceted problem.
And we've journeyed through an innovative approach to actually measuring this humanness using a powerful hybrid neural network that looks at both the spatial layout and the temporal flow of actions.
An approach that proved remarkably effective, at least in their study, at spotting the difference.
Yeah, it really highlights that making AI capable is one challenge, maybe the one we hear about most often, but making it believable, that involves grappling with a completely different set of nuanced problems.
Problems often centered around replicating our very human imperfections, our limitations, our specific ways of doing things.
Indeed. And maybe it leaves you, the listener, with this thought to consider. If AI development continues at its pace and gets so good that it can convincingly simulate human flaws, inconsistencies, moments of hesitation, maybe even idle actions, or something like emotional tilt during gameplay.
A believable simulation of irrationality.
Could the very methods designed to detect non-human behavior, like the powerful model we discussed today, start to become less effective over time? If AI gets really good at mimicking the tells, what does that mean for how we distinguish truly human creativity, strategy, or decision-making from highly sophisticated, maybe even flawed, imitation?
That's a compelling question. As AI continues its rapid advancement, where does imitation end and something else begin?
Something to think about. And that's the deep dive for today.